I hope you can hear me. And I thank ICTS and Acharya Institute of Technology for inviting me to give this lecture. And it's an honor to be giving a lecture under the banner of Einstein lectures. And I learned that these lectures were started to celebrate 100 years of Einstein's general theory of relativity. So I feel a bit elated, but I assure you that I'll keep my feet on ground and we'll be on talking terms. So I don't mean to give you a sermon, or teach you anything, but I just want to convey the beauty of this concept of boundary layer to you. So let's keep it interactive. If you like to stop me or ask something, feel free to do that. So, and I try to keep it as simple as possible, so you can sit back and relax. Okay, so the topic is really the concept of boundary layer and its prevalence in aeronautics. So, as I wrote in the synopsis, in 1904, 1 year before the miraculous year of Einstein, a German engineer, Ludwig Prandtl, and I guess at least some of you know the name of Ludwig Prandtl. He proposed the concept of boundary layer. And that actually brought in a silent revolution in the field of fluid dynamics. So before we try to understand, that concept, let's look at the background a little bit, the historical background. So as you know, for a fluid which is assumed to be continuous in space and time, the governing equation is the Navier-Stokes equation. So all of you at least will be familiar with the term Navier-Stokes equation. So it's a partial differential equation, and on the left hand side you basically have fluid acceleration multiplied by density. So this is the mass into acceleration term, and on the right hand side you have the net forces acting. So the Navier-Stokes equation is really an expression of the Newton's second law of motion applied to fluids. So there's a pressure force here, and there's a force due to viscous stresses. So mu here is the dynamic viscosity in the fluid, of the fluid, and these are the two operators. So this is a gradient operator. I'm sure you know basics of vector calculus, and that's the Laplacian operator. X, Y, Z are the three coordinate directions, and U is the velocity vector, rho is density, and P is pressure. Now these equations, were proposed in the mid 19th century, by Navier and Stokes. Now this is a strongly nonlinear differential equation, and actually this is one of the 7 Millennium Prize problems to basically prove the existence and smoothness of the solutions of the Navier-Stokes equations. So mathematically, it has not been possible to establish whether a solution exists to the Navier-Stokes equation under a fairly general set of boundary conditions, and whether these solutions are smooth. So it's an important problem in mathematics. Now, if you look at common fluids like air and water that we deal with, and you look at the numerical value of the viscosity, which is really the agency which causes friction in the fluid, and if you just look at the numbers, typically, now there is a quantity called kinematic viscosity, which is just mu by rho, the dynamic viscosity divided by density, and for air it's of the order 10 to the power minus 5, and for water it is 10 to the power minus 6. So because these are such small values numerically, it actually seems to make sense to neglect viscosity in the Navier-Stokes equations, and that results in equation for the inviscid flow, okay, which are called as Euler equations. So here we have just dropped the viscous term, okay, and this was actually proposed by Leonard Euler, and therefore these are called as Euler equations, okay. Now remember that although we have dropped the viscous terms, which are the second order derivative terms, the non-linearity is still there, because the non-linearity is really contained in this term, which is the so-called convective acceleration of a fluid particle. So you can see that it is u d dx of u or u d dy of u, which is a non-linear term. So you can classify differential equations as linear or non-linear. Okay, I will not go into that, but this is the non-linear term. Okay. Now it's possible to further simplify it. Okay, and for that we use a vector identity, which is written here. So this term, the convective acceleration term, actually can be expanded in these two terms. Okay, so it's just a vector identity. Okay, you don't have to remember it. You can find it in any standard textbook. So this is the curl operator, and it's u curl of grad. This is a cross product, and this is u grad cross u, curl of u. Okay, and that's the gradient operator. Now, curl of u or grad cross u is nothing but vorticity. Okay. Now, I don't know how many of you know what vorticity is. Okay. Any one of you, do you know what is vorticity? What does it represent physically? Yes? Yes, so it's the tendency of the fluid particles to rotate. Okay, so that is vorticity, and that is mathematically expressed as curl of u. Okay, so if we do that, and if we introduce it here in the equation, this is what we get. Okay, we have just substituted, and then this term we can take to the right hand side, combine it with pressure. So this becomes P by rho, pressure by density, into half u squared, which is the kinetic energy per unit mass. Okay, and that's the left hand term. Now remember, we are talking about inviscid flow because we have set the viscosity equal to 0. Now question is it possible to have vorticity in the inviscid flow? Okay, so is it possible to have a rotational, as he said, it's a measure of rotation. So is it possible to have a rotational inviscid flow? Or is it that the inviscid flow has to be devoid of vorticity or irrotational? Okay. So the answer to this question is that you can actually have inviscid rotational flows. So usually, if you want to generate vorticity, you need viscosity. Okay, in the simple incompressible limit. Okay, but it appears that the vorticity can exist in an inviscid flow, although it cannot be generated. Okay, so for example, if an aircraft is flying, it generates wingtip vortices. You all know about wingtip vortices. And suppose there's an aircraft following this aircraft, which encounters these wingtip vortices. Now these vortices will contain vorticity in it. So if you now consider a domain of flow surrounding this aircraft, okay, the vorticity will enter into the flow. And you can assume the flow to be inviscid. Okay, and that's what is done in aerodynamics as a first cut calculation. Okay, but then you will have to consider it to be a rotational inviscid flow. Okay, and in fact, in the mid of 19th century, there were important theorems with regard to vorticity and circulation that were proposed by famous names like Helmholtz and Kelvin. So it was very much, a topic of study around the time when Navier-Stokes equations were proposed. Okay, I will not, of course, go to the statements of these theorems. You see terms like vortex tubes and circulation, but you don't have to worry about that for now. So essentially, what this means that if the flow is irrotational as it enters here, when I say irrotational, I mean devoid of vorticity, no vorticity, it will continue to remain irrotational. Okay. So, if you now consider an inviscid irrotational flow, okay, you put omega equal to 0. That's the definition of an irrotational flow. Vorticity is equal to 0. And let's also assume the flow is steady. Okay, it's a simplification, but it is good enough to make the point. Then what you get basically is that both the terms are 0 on the left hand side, and the equation reduces to basically gradient of this quantity equal to 0, or this quantity is a constant. So is that a familiar equation to you? What does that equation represent? It's basically Bernoulli equation. So I do not know you ever derived it this way, but this is actually a very illuminating way, starting from the Navier-Stokes equation. You probably use control volume approach, starting from a streamline and taking a control volume around a streamline to arrive at Bernoulli equation. But this is a very intuitive way of arriving at the Bernoulli equation, starting from Navier-Stokes and making all the relevant approximations on the way. Okay, so that's the Bernoulli equation. Now omega equal to 0, which means curl of u equal to 0, again a consequence of vector calculus, is that you can express the velocity as a gradient of a scalar potential. Okay, so if you go back to your mathematics course, curl of gradient will be 0. Okay, identically. So you can express velocity as a gradient of a scalar potential, and that's actually called as velocity potential. Okay, phi. Now, if you look at the mass conservation equation, okay, for incompressible flow, it's del dot u equal to 0, right? Gradient of u equal to 0. So it's basically conservation of mass. So now if you substitute u equal to grad of phi, what you get is del square of phi equal to 0, right? Which is the Laplace equation. Now this is a linear equation. Remember, the Euler equation and the Navier-Stokes were non-linear equations. This is a linear equation, which is a considerable simplification. And this equation is actually obtained in other fields also. In fact, around the time, when the fields of electricity and magnetism were being developed. Okay, for example, if you take electric potential, if there are no charges, if there is no charge density in a given volume, then the electric potential is also governed by Laplace equation. Okay, so the Laplace equation was encountered in many different fields, in the mid 19th century, and therefore great deal of work was done during that time on getting solutions and building a theory around this. And in the context of fluid mechanics, this was called as potential flow theory. So because the velocity can be expressed as a gradient of a scalar potential or velocity potential, the study of this equation was called as potential flow theory. Okay, and this line of investigation, especially in the 19th century, was called as theoretical hydrodynamics or hydrodynamics, and this was mainly pursued by applied mathematicians and physicists, okay, in the 19th century. So this is what I refer here as hydrodynamics, okay, so one of the two disciplines. Now, if you plot streamlines for a potential flow past a cylinder, let's say, this is how they look. So it's a two-dimensional cylinder, okay, it doesn't change in the third direction. So they look symmetric, about both the horizontal line and the vertical line. Okay. So essentially there is no net force acting on this cylinder. I hope you see this point. Okay. Now if you put a spin on this, okay, or introduce circulation, or introduce a vortex right at the center, then it produces a spin. And that distorts the streamlines. Okay. And now you have a side force acting on it. And in fact, this is called as Magnus effect. And this is the reason why a table tennis ball experiences a top spin, or a football when kicked by a football player appropriately with a spin actually deviates from its linear path. So it follows a curved path. And it's essentially because of the side force due to the spin. And this can be very much understood in the context of potential field theory. Okay. So for example, the lift generated on an aerofoil can be understood in the context of the potential field theory. But then if you look at the real viscous flow past a cylinder, this is how it looks. Well, you can see a certain symmetry about the horizontal plane, but there's certainly no symmetry about the vertical line. Okay, so this is essentially the wake of a body because of the presence of viscosity. And then, depending upon the speed, you can also have unsteadiness in the wake. And this is the so-called von Karman vortex street. Okay, this is a beautiful pattern which is presented in the wake. But in any case, the presence of wake and the drag which a body experiences because of the presence of wake, which essentially goes back to the effect of viscosity, could not be explained in the context of potential field theory. So that gave rise to the so-called D'Alembert's paradox. Okay, and I'm rephrasing the paradox here. So the question that was posed was that how is it that a body moving through a fluid which has a very small viscosity, vanishingly small viscosity, 10 to the power minus 5 or 10 to the power minus 6, like air and water, how is it that such a body experiences a non-vanishing drag, a finite drag? Because when engineers did measurements, okay, on bodies moving through fluid, they actually measured considerable drag on these bodies, which could not be explained using the potential field theory. Okay, and engineers, in fact, wanted this information to design and build canals, dams, locomotives, gliders towards the end of 19th century. But then the potential flow theory was of little use. So what they did, actually, they conducted a variety of experiments or tests for every configuration. And they measured the various empirical constants, or you can call them as coefficients, such as drag coefficient, discharge coefficient, friction factor, etc. Okay. And this discipline was known as hydraulics. Okay. So hydrodynamics was something that was being pursued by physicists and applied mathematicians. And it was actually with an assumption that the fluid is essentially inviscid and irrotational. Whereas engineers pursuing hydraulics, they essentially dealt with real viscous flows. So the study of fluid flow was really divided into these two disciplines, or these two worlds. Okay, so hydrodynamics and hydraulics, and they were more or less two watertight compartments. And they looked at each other with a scorn, with ridicule. Okay, so hydraulics was termed as a science of variable constants. Now, how can a constant be variable? But it was sarcastically called a science of variable constants, because these constants changed. Every little change they wanted in their design, they had to make a new test and measure a new constant. Okay, so there was no underlying principle on which a new design would be arrived at. And the hydrodynamics was called as the mathematics of dry water because it dealt with inviscid flows, and in reality you don't see inviscid flows. So if you want to deal with water, it is bound to be wet, it cannot be dry. So this is a fascinating book which presents the history of hydrodynamics and hydraulics in the 19th century. So that was the backdrop, really. So the study of fluid motion was divided into these two worlds, hydrodynamics and hydraulics. And there was very little communication or overlap between these two fields. So it's under these circumstances that Ludwig Prandtl, a German engineer who was at the University of Hanover at that time, he proposed this concept of boundary layer in the International Mathematical Congress in Heidelberg, 1904. So the concept of boundary layer essentially is that however small may be the viscosity, like that for air and water, there always exists a thin layer close to the surface of a body, okay? And in that thin layer, the velocity gradients are large, okay? And therefore the viscous forces cannot be neglected. Okay? So you can have a fluid with very small viscosity flowing past the body, but there will always exist a very thin layer surrounding the body where the viscous forces cannot be neglected, and therefore the potential flow theory cannot be applied. Okay. So that is the essential idea of boundary. So it's a boundary. It's a layer present at the boundary of the surface. And this in fact bridges the gap, and we will see how, between these two disciplines. And it's actually, introduction gave birth to this discipline of fluid dynamics, which we study today. Okay. And it also basically solved Deilenberg's paradox because in that thin layers surrounding the boundary, the viscous effects are important. So that accounts for the presence of drag on the boundary. Okay. So the Deilenberg's paradox, which said that the vanishingly small viscosity results in finite drag, was resolved with this concept. Okay, so that's the original paper in German. Okay. It's about 12 pages paper. It's very terse, not highly mathematical. In fact, he presented his wind tunnel experiments there. I hope all of you know about wind tunnels. So he was an engineer, but he also had an acumen for mathematics and a very acute physical insight. There is also a translation in English which appeared in 1938. So it took time, for this idea to propagate. That's why I call it a silent revolution, because it took really nearly 50 years to establish this concept on a firm footing. But all the essential ideas were there in 1904 when he proposed this concept. So let's now take a look at what constitutes Prandtl's boundary layer theory. Let's look at it in verses. So let's do a poetic justice with this great idea. So let's start. Okay. So fluid flows along a solid surface, assumed to be continuous in time and space. So that's the continuum hypothesis. The fluid is continuous in time and space, and that's why we can use partial differential equations. If viscosity of fluid is very small in case, strong gradients don't allow its effect to be less. So that's what basic idea of boundary layer is. That even though the viscosity may be very small, the gradients can become very large. Now remember, the viscous force term is the viscosity multiplying this Laplacian operator, which really represents gradient of stresses. Okay. So although mu may be very small, if this term is large, del square u, the product may not be negligible. The product can be finite. So that was the basic idea. So let's consider an aerofoil and flow over the aerofoil. Let's take nu, which is the kinematic viscosity, to be small. Okay. Now, although this surface is curved, we will not consider the effect of curvature when we talk about the essential aspects of the theory. So we basically assume that if the boundary layer is present here, the thickness of the boundary layer is small as compared to the radius of the curvature. So, those of you who will soon be taking the boundary layer theory course, you will learn that this essentially is the first assumption that is made in Prandtl's boundary layer theory. You can of course introduce the curvature effects later on. Okay. So a thin layer near the wall called boundary layer, where the viscous stress is a dominant player. You already seen that. With the applications abundant and not rare, and I will show you, the myriad forms in which boundary layers appear in aeronautics, and of course they appear everywhere. Wherever there is flow past a body or flow through a body, like a pipe or a channel. Now this deserves special attention, but with a little care, and I tell you why it needs a little care, especially when you are dealing with the mathematics of this theory. Okay, so it's a highly exaggerated depiction of a boundary layer on this surface. So capital U is the oncoming velocity. Now remember that if you go far away from the body, in the outer inviscid flow, the velocity can change with x because of the shape of the body. Okay, and it's essentially because of the initial acceleration and further deceleration that you get peak suction on the suction side of an aerofoil, right? So it's really the shape of the aerofoil which causes the initial acceleration and then deceleration. So this u infinity into x represents that effect outside the boundary layer. So near the surface there is a thin layer called the boundary layer where the viscous effects are important. Okay. And that is, a paragraph from Prandtl's article in 1904, which actually got published in 1905. So, it's instructive, and in fact, the whole concept of boundary layer is condensed in this short paragraph. So let's read through it. So the most important aspect of the problem is the behavior of the fluid on the surface of the solid body. Sufficient account can be taken of the physical phenomena in the boundary layer between the fluid and the solid body. So that's the layer which is between the far fluid and the solid body. By assuming that the fluid adheres to the surface, okay, so that is the no-slip condition that you must have learned. So whenever a real fluid flows past a body, at the surface, the velocity of the fluid has to be the same as the velocity of the surface. Okay. So it cannot slip past the surface. It has to adhere to the surface. Okay. So that's what he says here. Although strictly it doesn't really adhere. It doesn't adhere as if there was a glue present between the two. But, well, in fact, I don't know if you are aware of that, but if you look at the molecular description of the fluid flow, actually the molecules do slip past the surface. They don't stick to the surface. Okay. But that slip velocity is so small that you can essentially neglect it. So the no slip condition within the continuum hypothesis is really an approximation. You should remember that. But for all practical purposes, and also for all theoretical purposes, within this approximation, it works very well. Anyway, so basically, I'll just read the last line. In this thin transition layer, which is the boundary layer, the great velocity differences will then produce noticeable effects in spite of small viscosity constants. So it's the viscosity multiplying the gradient of viscous stresses. So viscosity may be small, but the multiplying term can be large. Okay. So you cannot neglect this. Right. So now we assume the fluid far from the surface to be ideal, even though all the fluids inherently are real. All the fluids are real, what you encounter in practice. So it's an approximation again. The far field can be considered to be irrotational, since the vorticity terms are almost negligible. Now we saw that if there is no oncoming vorticity here, in an inviscid irrotational fluid, in an ideal, which is called as an ideal fluid, a new vorticity cannot be generated. So you can as well, although it is not strictly inviscid, because there is some viscosity there, but it's an approximation. So these, even if there are vorticity sources present, they are going to be negligibly small. So it's a good approximation to assume that it is irrotational outside, whereas within the boundary layer, the viscosity will be important. Okay, so now it's time to move forward and consider the equations that govern the boundary layer. Let's first make axis convention very clear. So x is along the surface and y is normal up there. So y is the normal to the surface, x is along the surface. So let's get back to the equations. The Navier-Stokes equations, which we wrote in the vector form, you can separate out the components. Okay. Let's consider a two-dimensional flow. So there's a mass conservation equation, there's an x momentum equation, there's a y momentum equation. So x is along the surface, y is perpendicular to the surface. Okay. And again, we are considering steady flow, so there's no unsteady velocity term here, no derivative with respect to time. Okay. This is the convective derivative, convective acceleration, and that's the pressure gradient force, and that's the viscous force. So, this makes it somewhat easier to appreciate. Right, so these are the equations we start with. Now let's introduce the scaling principle. That's an important concept in fluid dynamics or in physics in general. So, with u as reference velocity and length scale L, we'll talk about it in a minute. Another length scale delta, which is very less than L. So delta is the thickness of the boundary layer. Scales the y coordinate and is itself very crucial. So that's the crucial aspect of the boundary layer theory. So it says that the velocities tangential to the surface can be non-dimensionalized using capital U. Okay. You know what is non-dimensionalization, which is divide the velocity by some reference velocity, which makes it non-dimensional. Okay. But, for non-dimensionalizing distances, there are two choices available. One is the length of the aerofoil, it's the chord length, and the second is the thickness of the boundary layer, which is delta. Okay. So this is, I think, one of the most important observations which Prandtl made, that there are two inherent length scales in the problem. And in fact, this delta becomes very crucial in the analysis. So let's do this basic non-dimensionalization. Okay. So the tilde quantities are non-dimensional quantities. X tilde is x by L. So here now, so what I have presented is the standard way, or the conventional way of doing non-dimensionalization, where you just choose one length scale, one velocity scale, and just express all the distances and velocities as non-dimensional quantities. And the pressure is not dimensionalized like this. So you can introduce these quantities in the equations, and a slight rearrangement gives a form like this. Okay. So the viscosity appears as 1 over Reynolds number, and all of you must be familiar with Reynolds number in your basic fluid mechanics course, which is u velocity times length times the dynamometric viscosity. So it is 1 over Reynolds number. So in fact, when you non-dimensionalize an equation, the relevant non-dimensional parameters, they appear naturally in the equation, like the Reynolds number appeared here. Okay. So then comes a very important proposition. We've already seen the Reynolds number in this definition. So how do we define the Reynolds number? As inertia by viscous forces in time division. Okay. So Reynolds number is inertia by viscous. It tends to infinity if the viscosity is small. So if the viscosity is small, as mu tends to 0, Re will tend to infinity. Right? I hope you are with me so far. Okay. So this becomes very large, mathematically tending to infinity. It becomes singular parameter in the equation. So what is a singular parameter? Right. So that's the x momentum equation, Navier-Stokes. Okay. So as Re tends to infinity, okay, if you drop this equation, this term in the equation, you get Euler equation. We saw this before. So as mu tends to 0, Re tends to infinity, you can drop this term and you get Euler equation. So the singular limit implies that if you take the full Navier-Stokes equation, find its solution, and take the limit as you approach the surface or y tends to 0. So it's the limit of the full solution, which is obtained by solving Navier-Stokes equation without any approximation. So that is called as limiting solution of the Navier-Stokes equation. But now if you inverse this process and take the limit of the equation first, as Re tends to infinity. So the limit of this equation is the Euler equation. And then look at the solution of the Euler equation near the surface. Okay, they do not match. Okay. Because the Euler equation does not consider the effect of viscosity. And near the surface, the effect of viscosity has to be important. Okay. So the limiting solution of the Navier-Stokes equation is not the same as the solution of the limiting equation. Okay. And that is called a singular limit. You don't have to remember or understand everything, but it's a very important concept when you deal with the asymptotic limits. So Re tending to infinity is an asymptotic limit. Right, so we are now going to do an order of magnitude analysis, and it's a very powerful tool again. And this is what Prandtl employed to arrive at his concept. So what is that? So then we find that the gradient of velocity in x direction becomes very small as that in y direction. Okay. We'll see that why. Terms with the same order of magnitude are kept, and the remaining negligible terms are left. It is left out. So we are doing an order of magnitude analysis. But here now, what is an order of magnitude analysis? So we are going to say that x is of the same order of magnitude as L. So this similarity symbol means that they have the same order of magnitude. Okay. Which means if you take x by L, that ratio will probably vary between, let's say, 0.5 to 5. It will be, over a small interval around 1. Okay. So essentially what this means, it will not be exactly 1, the ratio, but it will not be so small as 10 to the power minus 2 or so high as 100 or so. It will be close to 1, essentially. So x is of the order of magnitude of capital L, but the y, okay, within the boundary layer is not of order L, it is of order delta. Okay? Because if you look at this figure, so the distances within the boundary layer y actually are of the order delta and not L. And in fact, delta is a very thin layer. So delta is much less than L. So that's a crucial choice for y. And then with this we can estimate d dx as 1 over L and d dy as 1 over delta. Because x goes like L, y goes like delta. Now because delta is much less than L, d dx will be much less than d dy. That's we have said here, that the gradient in x direction becomes much smaller as compared to y direction. Okay. So with this, the y momentum equation degenerates into a very simple relation. We are going to look at now x and y momentum equations with these choices of scaling variables, saying no pressure gradient in the y direction, a result very useful for further calculation. So now we have actually started looking at the boundary layer theory itself, and how the equations simplify and how we can approximate the equations within this theory. Okay. So we do the boundary layer, the order of magnitude analysis on the continuity equation and the two momentum equations. So what you do is you estimate the order of magnitude of each term in the equation. Okay. So we say that u, the streamwise velocity, is of order capital U, x is of order capital L. Now the wall normal velocity within the boundary layer, we do not know what is the order of magnitude of that. Okay, so we keep it as v. And for y, we use delta. Okay. So in fact, if we say that these two terms have to be of the same order, or they have to be comparable to each other, then these two have to be of the same order of magnitude, and therefore the v velocity has to be of this form. Okay, so the v velocity is less than u velocity by a factor delta by 10. So within the boundary layer, the wall normal velocity is much smaller as compared to the streamwise velocity. So that's what it says. And then it says that if you look at the y momentum equation and again estimate the order of magnitude of different terms. So for example, u goes like capital U, v goes like capital V, x goes like L, y goes like delta. For pressure gradient, we do not know how it goes like. Okay, so we keep it undetermined. Okay, now if you substitute for v from what we estimated here, then you can rearrange everything in this form, and you can see that each term multiplies, there is a multiplication factor delta by L, and we have said that delta is much less than L. Okay. So these are very small terms, and in fact in a moment's time we will compare this with the x momentum equation, and that will make it clear as to why these terms can be neglected. So essentially, if you now bear with me and consider these to be negligible terms, what this results is in dp dy equal to 0, which means the pressure does not vary in y direction. Okay. We will bring the x momentum equation into picture. So x momentum equation finally comes into picture. X diffusion term then makes its departure. You will see that pressure derivative term shifts from partial to total, and its expression from Euler equation becomes so simple. So because pressure doesn't change in y direction, the partial derivative actually becomes total derivative in x direction, because pressure is only a function of x now, not a function of y. So that's first simplification that we get. So pressure is constant across the boundary. Look at the x momentum equation. Again, do an order of magnitude analysis. Okay, and now I have also reproduced the y momentum order of magnitude terms. And now, when you compare with each of the terms in the x momentum equation, you will see that all the terms are less by a factor delta by L in the bracket, and so it was justified neglecting those terms. Okay. So now you look at these terms and divide by u squared by L. So the left hand side terms become order 1. Okay. And the right hand side term becomes 1 over RE here. Simple mathematics. If you are attentive, You will have noticed by now. I hope you are. And this becomes 1 over Re into L by delta squared. Okay. So now, as Re tends to infinity, okay, we saw the limit, asymptotic limit. It's very clear that this term will go to 0, just 1 over Re. But now, the question is whether this term will also go to 0. See, if that term also goes to 0, then it reduces to Euler equation, which is not very useful because then there is no viscous term present. So in fact, if this term has to be order 1, delta by L has to go like 1 over square root of Reynolds. Because then, if you take L by delta squared, Re by Re becomes 1. So this term is of the same order as the left hand side term. So that can be hated. Whereas the X diffusion term is ordered 0 as Re tends to infinity. So that has to be dropped. So that is the second simplification that you achieve. So in fact, you can write the dp dx term as total derivative, and you can drop the streamwise diffusion term here. Okay. And then if you evaluate this equation near the edge of the boundary layer, remember this u infinity is the velocity at the edge of the boundary layer. It actually reduces to Euler equation. So within the boundary layer, where the viscous effects are important, you get this equation. But just outside the edge of the boundary layer, the viscous effects can be neglected, the velocity gradients become very small, and it reduces to Euler equation. And because pressure doesn't change across the boundary layer, whatever pressure you determine from the Euler equation, the same pressure is imposed on the boundary layer and holds throughout the boundary layer. So in fact, this term can be replaced by this term, okay, because of the fact that dp dy is equal to 0. We are heading towards the end of this, okay, so you can bear with me for a few more minutes. I mean, mathematics is not boring, so you can try to be a little more attentive. So the Navier-Stokes equations that are initially elliptic, thus get converted into ones that are parabolic. See, this is where you can make connections to all that you have learned. I don't know if you have learned partial differential equations and their classification as elliptic, parabolic, or probably you will. With boundary conditions stated clear and specific, solutions can be obtained with methods that are classical. So just a small mathematical point, I will not labor on this, that the form of the equation, which is elliptic, you look at the equation of the ellipse, and this is something similar. It gets converted into a parabolic differential equation, like y square equal to PREVALENCE. So that is a considerable simplification for those who know what it is. Now here comes the crux of the theory, that this makes the theory almost complete, but in addition, the solutions have to satisfy the following condition: matching the outer limit of the inner solution with the inner limit of the outer solution. So, what does it mean? Now, you remember this differential equation is second order in U, in Y. Okay. So, how many boundary conditions will you need to solve the equation in Y? 2 boundary conditions. So, one boundary condition is of course at Y equal to 0 at the surface, no slip, no penetration. But then at large Y, what is the other boundary condition? Outside the boundary line. Okay. And that is actually given by the inner limit of the outer solution. Right? And what does that mean? So, we talked about the 2 worlds. Okay? The world of the inviscid rotational flow and the world of the real viscous flow. So, these are basically the 2 worlds. The outside world, far away, is ideal flow or potential flow. Inside the boundary layer, it's viscous flow. Okay. So somewhere in the intermediate region, the 2 solutions have to match. You cannot have a discontinuous solution. The solution has to vary continuously from the inner world to the outer world. So this is called as the inner solution, that is called as the outer solution. So you take the outer solution and come close to the edge of the boundary layer. That essentially provides the boundary condition for the boundary layer equations. So this is beautifully depicted by this painting by M.C. Escher, which is called as Sky and Water. So if you look deep in the water, you see the fish swimming. If you see high in the sky, you see birds flying. But if you see near the surface where the interface is, you see both the forms of the fish and the birds. So that's the continuous variation from the fish in the sea and the birds in the sky. So you have the inner solution and the outer solution, and they have to match intelligent. So that's essentially, in summary, the equations which resulted from the boundary layer theory. So continuity equation is there. X momentum equation has become simplified by this substitution, and these are the boundary conditions that we have to give at y equal to 0, away from the surface, and at x equal to 0. So we'll end this now. So an epilogue. So let's shower some praise on Ludwig Prandtl. So Diolembert's paradox thus had to wait for several years until Prandtl the Great. I hope now you realize that the physical insight that he had, with his genius mind and sharp intellect, could solve the problem to a great extent. I did not say completely, because there are still elements which it could not cover, but still to a great extent. So Prandtl thus, with his immense contribution, gave fluid dynamics a totally new direction. Many different avenues did his theory help open. In fact, the so-called inner solutions, outer solutions, and matching, it resulted in an entire new field of mathematics called the method of mass asymptotic expansions. So it, in fact, this very powerful idea resulted in many different avenues of research. So this really laid a solid basis for studying fluid motion. So that is the contribution.
So far we looked at the foundations of the boundary theory and the essence of the concept of the boundary layer. Now let's look at some instances of boundary layers in aeronautics. So we will see the different manifestations in which they appear in aeronautics. Of course, boundary layers will be present whenever there is a relative motion between fluid and any solid surface. Okay, so we just choose aeronautics as one particular field in which there are a variety of different ways in which boundary layers appear. So first, let's look at nearly two-dimensional boundary layer. So this is an aircraft with a rectangular wing, and if you look at the most part of the aircraft, away from the aircraft wing, away from the wingtip, as well as the fuselage, then you can expect the boundary layer to be two-dimensional. Of course, when you take a cross section here, which is an aerofoil section, for a large aspect ratio wing like this, the flow can be expected to be two-dimensional, but there will also be a pressure gradient present because of the shape of the aerofoil, and this is what results in the lift that the aircraft experiences, and which balances the weight force of the aircraft. So this so-called favorable and adverse pressure gradient, that is accelerating and decelerating effect the pressure gradient has, is felt by the boundary layer, and that's an important effect to take into account. Now, if you look at typical passenger aircrafts, there's a considerable sweep back of the wings, as you can see here, and therefore the boundary layer over such a wing is going to be three-dimensional over the entire wing. Okay, and there's one interesting phenomenon which happens here, which is the skewing of the streamline. So I've shown here three different streamlines, three different colors. So one is dark blue, green, and red. And before the streamlines enter the boundary layer on this wing, this is a top view. So seen from the top, they overlap each other. But as they enter the boundary layer, depending upon their height relative to the boundary layer thickness, where delta is the boundary layer thickness, they are deflected. So y3 is closest to the surface, it is deflected the most, and y2 is close to the boundary layer thickness, it is deflected the least. Okay, so this gives rise to considerable complexity for the three-dimensional boundary layers, which is not present for two-dimensional boundary layers. Another manifestation is an unsteady boundary layer, okay, where the flow changes with time. And a typical instance is when you have this propeller wake for a turboprop aircraft, for example. So the propeller wake or the tip vortices, which are highly unsteady, interacting with the boundary layer on the wing, which in fact results in an unsteady boundary layer. Another example is a pitching or flapping foil. For example, if you look at micro area vehicles which are motivated by bird flight, okay, you will see the unsteadiness because of the movement of the lifting surfaces. Another dramatic example of unsteady boundary layer is the gas turbine blades. So this is a cross section of a gas turbine, a section where the shroud is removed over this particular sector, and you can see different stages. So you have a fan, it's a turbo fan engine. You have compressor stages, turbine stages. So in a given compressor or turbine stage, you have a number of rotor and stator stages. So let me just run this video, and you can see that the wakes coming out of the stator stage, they are highly unsteady, and they interact with the boundary layer on the blades in the following rotor stage, and the same happens when this wake passes over the boundary layer on the stator stage. So this is a very highly unsteady sort of situation, much more complicated to understand. Okay, so next is a separated boundary layer, and this happens when the opposing pressure force is so large, okay, because of high angle of attack, that the boundary layer cannot stay attached to the surface, and it in fact separates from the surface. And this typically happens when you have an aerofoil at an angle of attack close to the so-called stall condition, okay, where the boundary layer separates, and in fact at the stall condition it separates over the most of the suction surface, and you see this large wake with its own complex structure present. So that is a separated boundary layer. And a striking example of a three-dimensional separated boundary layer is a delta wing, and that's a classical delta wing, a delta-shaped wing, capital delta, and that's a water tunnel visualization, beautiful visualization done in France by Verlet. And here, because of the sharp leading edge, there is separation happening right at the leading edge, okay, and it's also highly three-dimensional because of the large sweep back here. And this is a typical planform which is used for high angle of attack fighter jets. And this is one visualization where you don't have a conventional delta, but you have a strake with a rectangular wing, and you can see a phenomenon called as vortex breakdown, okay, that of course has its own consequences for the stability of the aircraft. Now another important type of boundary layer is a turbulent boundary layer, and I will in the next slide describe the distinction between laminar and turbulent flows. But if you have noticed on typical passenger aircrafts, you will see these little projections coming out, and they are basically there to promote turbulence, because a turbulent boundary layer is more robust in staying attached to the surface even when there is opposing pressure force or adverse pressure gradient. So you know that flows in general can be classified into two types: laminar flow and turbulent flow. So laminar flow is regular orderly flow you can imagine it in the form of layers moving one on top of the other, like a deep river moving at a slow pace, okay, shown on the left hand side. Whereas a turbulent flow is highly unsteady, irregular, chaotic, which shows high unsteadiness, three-dimensionality, high mixing and dispersion, etc. So is somewhat similar to a shallow rocky river in mountains moving at a fast speed, okay, on the right hand side. And a process by which a laminar flow becomes turbulent is called as transition. So this is the schematic of a boundary layer, which is first laminar, then it becomes transitional, and then becomes turbulent. Okay, so this is a fully turbulent boundary layer here. And if you look at most of the technological applications, especially in aeronautics, the flying vehicles, then if you calculate the Reynolds number based on the wing chord, which is this distance, let's say mean wing chord, and I've chosen a typical Airbus 320 aircraft here, you get Reynolds numbers of the order of 10 to the power 7. And Reynolds number is a typical parameter characterizing the switch from laminar to turbulent flows. So low Reynolds number, you are likely to find laminar flow, high Reynolds numbers, turbulent flow. And whenever a turbulent boundary layer is present on aircraft wing or fuselage, there is considerable higher skin friction drag that the aircraft experiences. And in fact, for typical passenger aircrafts, this drag is about half of the total drag on the aircraft. So it's quite important that if you are able to control the turbulent boundary layer somehow, okay, so that it leads to a reduced drag, then that translates into a reduced fuel consumption and finally into reduced emission. Okay, and therefore we should be able to realize a greener aviation with less emissions and also which is more economical. So it's quite important, in fact, to understand and to be able to manipulate these turbulent boundary layers. Now, the reason why the skin friction at the surface for a turbulent boundary layer is higher than that for a laminar boundary layer is that the turbulent velocity profile within the boundary layer is quite full close to the surface as compared to a laminar profile, okay, which means du dy at the wall, which is y equal to 0, is much higher for a turbulent boundary layer, and therefore the shear stress at the surface is much higher. And if you now open up and look at what constitutes a turbulent boundary layer, what it is composed of, you can describe the motion in terms of the so-called eddies. Okay, and these eddies in fact cause an increased transport of momentum towards the wall. Now, one way of looking at these eddies, which has especially emerged in the last 2 or 3 decades, is the so-called coherent motions. Okay, so these are orderly, relatively more regular kind of patterns or motions, which are present, which are buried within the apparently chaotic eddy motions, which a turbulent boundary layer is characterized by. Okay, and then there are different techniques to identify these, to understand how and where they are present within a turbulent boundary layer and what kind of contribution they make to the skin friction. So this continues to be an important area of research even now. Okay, and in fact these areas and all of them that I described, in fact, in the context of aeronautics, are areas of current research. And remember that even when Prandtl looked at the behavior of the flow close to the surface to introduce his concept of boundary layer, he was looking at it as a research problem. So all these advances, in fact, have taken place through research. So when you combine the research and discovery, you advance the field of science. When you combine the research with invention, you advance the field of technology. Okay. So what is at the heart of these endeavors is research. Right. Now, you could also have instances where the Reynolds numbers are intermediate to laminar and turbulent regimes, and then you get a transitional boundary layer. So, for example, an unmanned aerial vehicle which has a short chord, much shorter than these large passenger aircrafts, typically experiences transitional boundary layers or transitional Reynolds numbers. Same is the case with wind turbine blades, which operate at relatively low speeds. Okay, so you will find that the boundary layers present on these surfaces are transitional, neither laminar nor fully turbulent. Okay, so these are basically some of the instances just to give you a feel for the the variety of applications that the boundary layers have in aeronautics, and also to show you some colorful pictures. Okay, so let's conclude here. So what's the takeaway message from what we have discussed? Um, we started looking at the concept of boundary layer, okay, and in fact, to understand the physical idea behind it. So try to understand the origin of important concepts like that of a boundary layer, and then appreciate the far-reaching consequences they lead to. Okay. In fact, the boundary layer concept itself enabled opening an entirely new field of mathematics, apart from giving birth to this field of fluid dynamics. Don't get lost in details. Okay, you can always apply this concept to a particular situation to get detailed information about that. So remember Einstein's quote. He said, "I want to know how God created this world. I'm not interested in this or that phenomenon in the spectrum of this or that element. I want to know his thoughts. The rest are details." Okay. So try to go to the core of any issue and to understand the central message. We have seen the interplay between physics and mathematics. Okay, when we looked at the development of boundary layer equations, starting from Navier-Stokes equations. So don't shy away from mathematics. Try to interpret a governing equation in terms of the physical effects it represents. Okay, then you will be able to see through the equations, in the sense what the different terms in the equation represent, and what are the important terms that should be retained in a given situation, especially a complex situation. And in fact, Ludwig Prandtl was a master at this, to see through the equations. And all this has been, as I said, an outcome of the research endeavor. So it is a fascinating endeavor. It is as rewarding as it can be frustrating. Yes, you need a lot of patience, perseverance, but it's also enjoyable. So it's not a bad idea for you to choose as a profession, or at least consider doing that. I invite you, in fact, to choose it as your profession. Okay, thank you for your attention.